Hello everyone, in this video we will be looking at more examples on our first topic, which is centroid of a plane region. So before I present to you the additional examples, let us first recall the center of mass of a lamina or the centroid of a plane region. This is a point on the lamina which serves as its balancing point. Meaning, if you place the pin underneath it, the sheet would stay level without tipping. So that's illustrated on the image on the screen. And now the next question is, how do we find the center of a mass? We need the information of the following. We have first the mass of the lamina. We also need the moment of mass about the x-axis and the moment of mass about the y-axis. We already talked about this when we looked at the application center of mass. Now, these formulas were derived during our class discussion. I will no longer explain that here in this video. Instead, we will just be using these formulas in answering our examples. So there are two ways in finding the centroid of the plane region. First is using vertical rectangles. So if we use vertical rectangles, like in this case, the mass, the integration will be in terms of x, right? And the mass is just density times the area of the region. So this is density times the area between two curves. We already know that that is integral of the upper function minus the lower function from a to b. Now the moment with respect to y is just the mass of the lamina, so simply this one here, so that's rho integral of f of x minus g of x times the location of the lamina, which is x. The moment with respect to x-axis is given by mass times the location of the lamina with respect to x-axis. So this part here is the mass times the location of the lamina, which is the average f of x plus g of x over 2. Now, finally, the centroid is the ordered pair x bar y bar, where x bar is just the moment with respect to y divided by the mass, and the y coordinate of the centroid is moment with respect to x divided by mass. Now, the second way of finding the centroid of a plane region is using horizontal rectangles. If that is the case, the integration will be in terms of y. That is why we have here dy. So the same. Similarly, the mass is just the linear density times the area. The area in this case is the function on the right minus the function on the left, which is g of y. That's why we have here f of y minus g of y. Moment with respect to x-axis is just the mass, so that's rho times this part here times the location with respect to x-axis, which is y. The moment with respect to y-axis is just the mass, so that's rho times the difference f of integral of the difference of the functions f and g times its location which is f of y plus g of y divided by 2. And finally, the centroid is x bar y bar, where x bar is the moment with respect to y divided by m, and y bar is the moment with respect to x divided by m. So now you simply have to remember these formulas, and after that, we are ready to do this example. Find the centroid of the region bounded by the curves y equal to x, that's the line, and y equal to 1/2 x squared, referring to the parabola. First, let us solve this problem using vertical rectangles. So if we use vertical rectangles, then our integration will be in terms of x from 0 to 2. So let me write that here. Using the vertical rectangles. Next, we look for the mass. So the mass is m equal to linear density times the area of the region. Since we used vertical rectangle, then this will be, the area is just the integral of the upper minus the lower function. So the upper function is defined, or the upper curve is defined by the function y equal to x, while the lower curve is defined by y equal to 1/2 x squared. So plugging that in, we have here integral from 0 to 2, referring to this interval here, of the difference of the upper function minus the lower function. Integrate with respect to x. Now we can integrate. So we have x squared over 2 minus 1/2 times x cubed over 3, evaluate from 0 to 2. Substituting, we have here rho. When x is 2, we have 4 over 2 minus 1/2 times 8/3. So I have here rho times 2 minus 4/3. So I have rho 6 over 3 minus 4 over 3. So therefore mass is given by 2/3 rho. Next, let's look at the moments. Starting with the moment with respect to y, denoted by m sub y. So it's just the mass. So exactly this integral here. So you have rho, integral from 0 to 2 of x minus 1/2 x squared dx times the location with respect to y-axis, which is x. So you can go back to the formula now to verify this one. Now multiply x, so I have rho 0 to 2. Distribute x, so I have x squared minus 1/2 x cubed dx. The antiderivative is given by x cubed over 3 minus 1/2 times x to the 4 over 4. Evaluate from 0 to 2. Now when x is 2, the upper limit of the integration, we have here 8/3 minus 1/2 times 2 to the 4th is 16 over 4. So rho 8/3 minus 2, which is 6/3. Am I right? Yeah. So finally, the moment with respect to y is given by 2/3 rho. With this information, we are now ready to find the x-coordinate of the centroid, which is just moment with respect to y divided by the mass. The moment is given by 2/3 rho divided by the mass, which is 2/3 rho. So the x-coordinate is 1. Now, let's proceed to finding the moment with respect to x-axis. So it's just the mass, which is rho, integral from 0 to 2 of the difference x minus 1/2 x squared times its location, which is the average, x plus 1/2 x squared. So change lang natin to, this part here, and divided by 2 dx. Multiplying, we have rho over 2, integral from 0 to, using FOIL, we have x squared minus 1/2 x no, minus 1/4 x to the 4th dx. Finding the antiderivative, we get x cubed over 3 times 1 minus 1/4 times x to the 5 over 5. Evaluate from 0 to 2. Substituting, I have rho over 2 when x is 2, so I have 8/3 minus 8/5. So I have here rho 4/3 minus 4/5. The LCD is 15. So 20 minus 12. So the moment with respect to x is given by 8, 15 rho. Thus, the y-coordinate or the y-coordinate of the centroid is given by m sub x over m. This is equal to, how do you call this? Mx is 8 over 15 rho divided by the mass, which is 2/3 rho. This will cancel out. So I have 8 over 15 times 3/2, which gives you 4/5. So the centroid is the ordered pair 1 and 4/5. That's it. Now let us solve this by considering horizontal rectangles. So if that is the case, then our integration will be in terms of y from 0 to 2. Let me write that here, horizontal rectangles. Let's start by finding the mass. So the mass is given by rho, integral from 0 to 2 of the difference of the rightmost function y equal to 1/2 x squared. Solving in terms of y, we have 2y, so x squared is x is given by square root of 2y, or x is square root of 2y to the 1/2. Let me close that. And the left hand side of the function, of the region is given by x equal to y. So therefore, the mass is linear density times the area, which is integral from 0 to 2 of the right hand function minus the left hand dy. Now taking the antiderivative, so we have rho square root of y to the 3/2 over 3/2 minus y squared over 2. Evaluate from 0 to 2. So I have rho when y is 2. This is square root of 2. I will have square root of 2 cube times 2 over 3 minus when y is 2 here, this is 2. Okay, let's simplify. So we will have here 8/3. Rho is equal to 8/3 minus 6/3. So the mass is 2/3 raw. Let me see if it's the same in the previous slide. Yeah, it's the same. Now let's find the moments using horizontal rectangles. So denoted by m sub y. So I have raw times, actually it's just mass times the location with respect to x-axis. So it's this part here times the location with respect to y-axis, which is the average. I have here raw sub 2 from 0 to 2. From the mass, I have square root of 2y to the 1/2 minus y times the sum, which is square root of y to the 1/2 plus y dy. Multiplying, I get raw over 2 integral from 0 to 2 times 2y minus y square dy. You can do FOIL here or use the special products. Okay, let's continue. Antiderivative, I have raw over 2 times the antiderivative is 2y squared over 2, so that's just y squared. Antiderivative of y squared is y cubed over 3, evaluate from 0 to 2. So when y is 2, I have here 4 minus 8/3. So multiply 1/2, so I have raw times 2 minus 4/3. Thus, the moment with respect to y is given by 2/3 raw. And the x-coordinate of the centroid is moment with respect to y times mass. So that's 2/3 raw divided by the mass, which is also 2/3 raw. So this is 1. Finally, let's find the moment with respect to x-axis. So this is just mass times its location with respect to x-axis. The mass is raw. Integral from 0 to 2 of square root of 2y to the 1/2. I'll just copy. Times its location, which is y. Review the formula to verify this. So you have raw, integral from 0 to 2. Distribute y, so I have square root of 2y to the 3/2 minus y square, integrate with respect to y. So the antiderivative is just square root of 2y to the 5/2 over 5/2 minus y cubed over 3, evaluate from 0 to 2. When y is 2, I get square root of 2 times square root of 2 to the 5 times 2 over 5 minus 8/3. Let's see what we will get here. So square root of 2 to the 6. So 2 times 8 times 2, 16. So raw is 16 over 5 minus 8/3. So LCD is 15. So 48 minus 40. So I get here 8/15 raw. So therefore, x bar is just moment with respect to y. Oh, sorry. We already have x bar. So let's find the y coordinate of the centroid. So that's moment with respect to x over m. This is 8 over 15 raw over the mass, which is 2/3 raw. So this is 4/5. So the centroid is the ordered pair. Oh, sorry. the ordered pair 1/4. So 1/4. So it's somewhere here. Let me use the black color somewhere here. Okay, so that's it. So look at more examples tomorrow. So in the meantime, please master